Hello everyone and welcome back to this new video. So in our previous video we looked at the high level or theoretical part of the sequence-to-sequence architecture. So today we're going to open up this black box and going to look at the specific linear algebra and probability theory that allows a machine to translate hello world into Bonjour le monde, which was the example of our previous video. We will trace the actual numbers as they flow from discrete text into continuous vector space and then back again after doing the translation. So the goal, first let's define our mathematical objective. The machine translation is essentially a conditional probability problem. We're not just generating random French words, we're looking for the specific sequence of words that maximizes the probability conditioned on our input x. In this example, our model considers many candidates. For example, Salut monde might have 12% probability, but Bonjour le monde has a 85% probability. Our mathematical goal is to train a model that assigns this highest mass to the correct translation. So to do that, the first step would be input embeddings. We start with the input. Neural networks cannot do math on strings, obviously. They only understand numbers. So we must convert the string into numbers. We use an embedding matrix denoted here as W embedding, EMB. We look up hello and retrieve the vector 0.1, 0.2. We look up word and get minus 0.5, 0.9. In real model like the one in the paper published by Google, these would be 1000 dimensional vectors. But for this presentation, we'll stick to 2 dimensions so we can track the math easily. Embedding is a whole big subject that we need to study separately to understand. It's also based on neural networks, deep learning, on how to translate or convert strings into numbers or vectors. Okay, so now in the encoder step at T1, now the encoder begins. We feed our first embedding hello into the LSTM at time step 1. So the previous hidden step would be empty. It's usually a 0 vector because there's nothing and we're just starting. And then the LSTM performs its internal gate operations like the forget input output gates. Remember that it like calculates the long-term memory, how much should we keep of that, the short-term memory, how much should we keep, etc. And then it would combine the previous hidden state with the current one. The hello vector 0, 1 and 0, 2, let's remember, it's this one here. So the result is our first hidden state, which, for example, let's say we get these values 0.3 and 0.15. The network has now consumed the first word. And now at the T2, this is where the magic of the recurrence happens, or the memory. We input the vector for the word, but we also input the hidden state from the previous step. So it's not just zeros, is the previous output, which was 0.3, 0.15. The network has now, and after doing the calculations, of course, the network has this output 0.85 minus 0.6. This specific vector now represents the phrase word contextualized by the word hello. So this would represent hello world. This final state is what we call the context vector. Again, if you remember from the previous video, it is the bottleneck of this architecture. Whether the input was short greeting or long paragraph, the encoder must compress the entire semantic meaning into this fixed size vector. In our example, the vector 0.85 and minus 0.6 is the mathematical representation of the abstract concept of hello world. And now we start with the decoder. After crossing the bridge, remember we have encoding, context vector, and then decoding. The encoder has finished its job. We take that context vector and use it to initialize the hidden state of the decoder. This arrow represents the only transfer of information between the languages. So the decoder starts its life already thinking about the concept. We start by 0.85 and minus 0.6, not like in the encoder we start with the 0 vector. If this vector is bad, the translation would be bad, obviously, and that's what we expect in the first iteration before doing the backpropagation and all of the training loop. So the first step of the decoder acts as a language model. It predicts the next word given the history. But at the first step, there is no history, so we feed the specific or special token, SOS, or start of sentence. So the decoder combines this token with our rich context vector to produce its first internal state. Let's say after doing all the calculations, we get this 0.9 and minus 0.10. And now the 0.9 and 0.10 is just a hidden state, it's not a word. To get the word, we project this vector into the size of our French vocabulary using a linear layer or dense layer. This gives us the log_its, which we pass through Softmax function. In our example, the model assigns 92% probability to the French word bonjour. It effectively says, given that I started with the context hello world, the most likely first word is bonjour. That's what we're effectively saying using the linear or dense layer. So this autoregression or the feedback loop, now that we have the word bonjour, the output at time t, which is this word, becomes the input at time t plus 1. So in the next iteration, the next step, bonjour would be the input. Remember the previous one, the input was the special token SOS or start of sentence. We take this predicted word bonjour, look up its embedding. Let's say it's 0.6, 0.4, and feed it back to the long short-term memory network to update the state. This is the previous state, with this one we get this new state of 0.2, 0.95. The model is now asking what comes after bonjour, even like the context hello word. Again, we repeat the cycle at t2. The model predicts le. We do that again. It would at t point equal 3. It predicts monde, and then we keep doing that until we predict the special token EOS, or end of sentence token. This is crucial as it allows the model to stop generating. Note that we put 2 words, but we get 3 words as an output plus this stop token. So the math successfully handled the length mismatch. Also, we can see the teacher forcing method. Quick note on how to train this. During training, our untrained model will make mistakes, obviously. Let's suppose at step 1, it predicted, let's say, chat. It's the French word for cat instead of bonjour. If we feed this word to the next step in the LSTM, the rest of the training sentence would not make sense. So to fix this, we use teacher forcing. During training, we ignore the model's guess. We mathematically force the input of the next step to be the ground truth word, which is bonjour. This stabilizes training significantly. So even if the LSTM predict that the next word is chat, given the context vector and the input, we would manually, let's say, force it to be bonjour, that would pass into the next LSTM. So we don't lose a lot of computing power and time in the wrong sequence. Again, this is more explained in depth in the previous theoretical video. Okay, now for the loss computation. How do we update the weights? We calculate the cross-entropy loss mathematically. We look at the probability the model assigned to the correct word. Here it assigned 0.92 or 92% to bonjour. The loss is the negative log of that number, which is very small, 0.08. If the model has been unsure and assigned only like 0.10 to bonjour, the penalty would be massive, 0.2. So this is the correct guess. This is the wrong guess. We use backpropagation to try and minimize this value or this value and make it as small as possible by updating the weights and biases. Now we can see this optimization trick that we've seen also in the previous video. It's from the original Google paper. Like they found that reversing the source sentence, feeding like word and then hello instead of hello world, will boost the performance greatly. Why? Look at the this red arrow. By putting hello at the end, it is right next to the bonjour in the time sequence. So we made the first word in the English language as close as possible to the first word in the French language. This reduces the time lag, making it easier for the gradients to flow from the output from the output back to the relevant inputs during optimization. So in conclusion, we have seen how text become vectors. We didn't see how, but we've seen the concept of embedding, how LSTMs compress the meaning, and how probability distributions generate translations. While this architecture revolutionized NLP in 2014, it struggles with the very long sentences because of that fixed sized context vector, or the bottleneck that we mentioned. In next presentations, we'll see how attention mechanism break this bottleneck. So that was it. Thank you for watching, and please subscribe.